Hello everyone, and this video is about simple machines, and really this is the fundamentals of engineering. It's way too simple for any engineering course, but this is the way that humans first learned to apply forces and to gain a benefit from using objects and mechanical devices to do different kinds of work. So, at some point way back in time somewhere, a human used an object to change the way their muscles applied force. So we can see here some old knives from the Paleolithic era, the very first sort of tools that humans used, and these are just bits of rock that are in a certain shape, but you can see how they might have been held very carefully between two fingers to carve bits of wood maybe, or something like that. So sometime shortly after that, they or somebody else really began to understand the principle that had led to the change in the force, and this began the field of engineering. So, forces affect objects, and if we want to do any task, we need to create a force. So, as humans, we are limited in the forces we can create. We have muscles, we have hands, we have arms, etc. So, the simplest machines are things that a person can use, and that changes the way that the person's muscles apply force. You can see here an example of people ploughing the ground by hand. And so later on we learned how to use animals, and we used the power of their stronger muscles to apply even greater forces, and used machines to do that. And you can see here a more advanced kind of plough, until finally we designed real, what we would recognize as machines today, that do work from energy taken from the world around us. And there's an example of one of the earlier forms, a windmill, taking wind energy from the weather in order to turn a wheel, and then we use that energy to grind grain or something like that. Obviously, since then, we've gone on to far more advanced machines than this windmill. So, if we're talking about machines and the way they apply forces, then we should also talk about mechanical advantage. You will see that some simple machines help us by lowering the force, the amount of energy we need to put in with our muscles or with some other means. And this is what we call mechanical advantage. And we can calculate the mechanical advantage. We can put a number on it. All we need to do is measure the amount of force coming out of the machine compared to the amount of force going in to the machine. And this will give us a number, basically a force multiplier, on what advantage this machine is giving us. So notice that it's a force divided by a force, and what that means is, unlike many other quantities in physics, mechanical advantage has no unit. Force is measured in newtons, and so we have newtons on the top, newtons on the bottom, and so those units cancel each other out. So we end up with a dimensionless quantity, mechanical advantage having no units. Also, you can see that you can have a mechanical disadvantage if the mechanical advantage is less than 1. In other words, if the output force is actually smaller than the input force. Now, why might you want to do that, you might ask, and I guess we'll see why we might want to do that in a few slides' time. Before we move on though, let's also think about something called efficiency. So no machine perfectly transfers the energy that is put into it. Something is always lost. So in a mechanical process, the energy is lost by the process of friction. And you may have heard of this. It's what makes your hands warm when you rub them together. So if we think about the principle of conservation of energy, the idea that energy can never be destroyed. You can never have less or more energy at the end than you had at the start. So what that implies is that the power going into a machine is going to be equal to the power coming out of it plus the power lost in whatever friction is in the machine, because the total amount of energy should be the same. And so if we give the efficiency as a ratio, which is the power out over the power in, then we get a number between 0 and 1. This will be just a proportion of energy, the amount of the total energy that went into the machine that actually gets used as work. And if you multiply that by 100, you will have a percentage for the efficiency. And no machine is 100% efficient. So just quickly to mention that we have talked about power kind of out of the blue here, and we will go back to it, but consider that work, power, and force are all related. They are all what is called directly proportional to each other. So it's time to start talking about the machines themselves, and the first one, you might not even think of it as a machine. It's the wedge. It transfers a horizontal force into a vertical force. So you can see here, if we move the grey wedge to the right, it's going to push under the wooden block and force it upwards, thus creating a vertical force from the horizontal force that was originally put in. So in an ideal world, a 45-degree wedge like this would transfer 1 Newton horizontally to 1 Newton vertically. But of course, we don't live in an ideal world. We have friction to consider. This is going to be a big problem, especially for steep wedges like this one. So if we want to use wedges a bit more easily, we can make them longer, which allows us to put in a smaller force because we are doing small bits of work at a time. We're lifting the block more slowly. However, we have to put that force in over a longer distance. As you can see, the wedge moves a very long horizontal distance, and we only get a very short amount of vertical movement from the wooden block. So wedges can be made more effective if you make them longer, but you'll need to apply the force over a longer distance. So the next machine we're going to talk about, again, doesn't really look like a machine. It's a ramp, often called an inclined plane. So a ramp is similar to a wedge, but essentially the force is applied to the object and not the wedge itself. So there, the input distance is how far you have to push the object up the ramp, and the output distance is how much you lift the object against gravity. So as before, you're basically just lifting it a little bit at the time, but you don't have to put effort into keeping it at the height you've moved it to, and then you can have a rest and try again. But if you were to try and put it directly into the truck, you have to be able to lift it vertically up to the output distance in one go. You can't stop, and you can't sort of keep it there and wait until you're ready to put another amount of energy in. So the ramp allows us to overcome gravity with smaller forces applied over a longer distance, and the mechanical advantage is based on a comparison between how long the ramp is compared to the height. So this is the length of the ramp. Note, not the base of the ramp, but the actual length of the distance we're pushing it, divided by the height that you are lifting the object to. So the next machine on our list is a screw, which is basically a ramp wrapped around something. If you want to push something up a circular object, you go around the outside, you're going to need a circular ramp. You might also be able to see in the background here, there is a water screw, which is something you can turn to lift water up a cylindrical twisted pipe. So the principle of the screw is it changes a linear force into a rotational force, or vice versa. So we turn the handle on the water screw, and that is a rotational force, but the water moves up the pipe in a linear motion, in a line. So what we also use a screw for is something called a screw, and this is perhaps the most obvious use of this machine in everyday life. And you can see there the screw, which looks a lot like a ramp in this picture, around the cylindrical body of the screw, and when you turn that with the screwdriver, then the ramp will pull the screw into the wood, and that will hold it in place. You can also consider that the screwdriver uses the principle of a wheel and axle, which is another machine we will be looking at, in concentrating the rotational force of the workman's hand into that very small cylinder at the bottom, into the screw head. So we'll just leave off there for this video, but you can join me in the next video where we will complete our little look at simple machines. Bye bye for now.